talked about energy and ecosystems, and now we're going to apply that information and evaluate relationships in ecosystems. So what I would like you to do, class, is please take a look at the learning target and turn to your partner and discuss the red highlighted words and what you think you know about them. And on your note sheet, there's going to be a section where you can jot stuff down, and so you'll have about a minute to do that, and I'll come around and see how everybody's doing.
Yeah, you can. Thank you, partners. You're welcome. Partner. Okay, so within class, I can draw evidence from 3 pieces of informational text to investigate ocean acidification as an adverse human impact on the environment, and be able to determine the meaning of symbols and key terms. Okay, so should we go in the order up there or the order here?
Let's go with chemical equations over here.
So it shows that there's the meaning of symbols, so obviously it's symbols representing chemical reactions.
Okay.
Yes.
Ocean
Any questions? Maybe drawing evidence?
No, frost burn. And oceans are the things beside the continents.
Acidification means that it's happening, so the process of like increase or something. So is it the addition of acid to the ocean?
I like that. Let's go with that.
You can draw down your ideas. But I'd like you guys to stop for a second. And so we're going to talk about some of these as we go along, but the one that I really want to talk about now is drawing evidence, because that's something you're going to have to do in this lesson today. So I would like maybe a volunteer to give me an example of what they talked about with their partner. Alyssa.
We did not talk about drawing evidence, but we talked about ocean acidification. And we knew fication was the addition of something, and since it was working on acid, we said it was adding acid to the oceans.
Okay, cool. So we got an adding ocean or acid to the ocean for ocean acidification. Does anybody, do we have a drawing of this, Robin?
When we talked about how we find evidence in our English classes to support what it is that are the things that we find out about something, so that we need to find specifically in our text what we're using to support what we figure out.
That's great. So we're going to find things within the presentation and the text we read later to support an argument that we will be developing later in class. All right. So the first thing I want everybody to be familiar with before we start today is identifying chemical equations. So as you see up there, we've got our lovely definition. A chemical equation is a written expression for a chemical reaction. So in this first equation on the top, we've got a left side and a right side. And I don't know if anybody's familiar with chemical equations, but is it possible that somebody knows what happens on the left side of an equation? What do you think, Mallory?
Aren't those the things that are going to be reacting together?
That's right. Those are the things that are going to be reacting together. And on the right side of the equation, Alyssa? Products? Products. That's right. So we have the 2 chemicals that are going to react to create some sort of product. The second equation here kind of goes over some fancy additions to chemical equations that we're not necessarily going to have to understand today, but they're good to know about. So those are, the first one, we have the coefficient, so that goes in front of a chemical and it tells you the quantity that you have. And that same thing happens with the subscript. It's the quantity of the chemical that you have. And then charges are electrons that are occurring in the equation. And it's important to know that the quantities and the charges stay consistent throughout the entire equation. So you can see here that the charges plus and the minus end up becoming neutral in the product. Yeah, Megan?
Why do we have 2 different ways to write quantity?
To right quantity. So the reason why you have a coefficient here is because you have the individual element x. So I could say I have x of this x. So you could pretend that little x is a 2. So I have 2 x elements. But when you see it on the product side, you still have 2x, but you don't have 2y. So you're saying I only have 2x and then I have 1y. So that's why you would have a subscript versus a coefficient. All right. So we are going to practice making our own fun reactants and products. And today that is going to look like my first example. Cheese and eggs gives you cheesy eggs. Or perhaps yellow and red gives you orange. So this is kind of just a general, like you have 2 different things and you're adding them together to get a final product. So you have your 2 things reacting to get a product. So work with your partner for 30 seconds to see if you can come up with something that utilizes 2 reactants to get 1 product. A different example.
A lion and a tiger equal a liger. I'm sorry, I just realized it was like, wait,
That's a good one.
I was watching Harry Potter, so I saw weird creatures.
What's the funky dog? Like a poodle and a golden retriever gets like a Labrador.
A golden retriever.
So we're making our own.
I'm gonna do that one. Poodle, this, golden
What if you don't think of anything else, but it's fine. More coefficient.
I can't swallow the noodles today.
My son plus his money.
Yeah, I'm just thinking about the noodles.
Strawberries and peanut butter. Peanut butter and jelly.
I did the strawberries and
Well, you might need some bread in there too. So you need to think about everything that you're going to have to
That's
add.
a good point.
So you might have more than just 2 reactions or reactants.
There you go.
All right, we're gonna wrap it up because we are a little strapped on time today. But I heard some really good reactions, and maybe Megan would like to share hers with us.
Okay.
Because I was pretty excited about that.
So we had coffee plus milk gets you a latte, or if we add a coefficient in front of coffee, we do 2 coffees or 2 shots plus milk is an extra strong latte.
Yeah. Good job, guys. All right, now we're going to segue into that topic of the day, which is ocean acidification. And I noticed that you guys were really discussing, like looking at the 2 parts, ocean and then the acidification. And I think Alyssa talked about cation was adding to something. So we might be adding acid to the ocean. And as you can see, it is the long-term decrease of ocean water pH caused by carbon dioxide emissions dissolving in the ocean. Which is pretty fancy information going on here. Does anybody know what pH is?
Is that how acidic or basic?
Yeah, it's a scale of how acidic or basic something is. And when you have a low pH, it's an acidic environment. So, and then also, how about carbon dioxide emission? Where would carbon dioxide emission come from? What do you think, Britta? Cars, yeah.
Burning the forest.
Burning the forest. So burning fossil fuel. Yeah, James?
People breathing.
People breathing. Yeah, there's some CO2 that's involved in that. So those are all great ideas. So it's talking about the ocean pH is slowly becoming less, so it's getting more acidic over long periods of time because of these carbon dioxide emissions from cars or breathing, or probably not so much the breathing, but the big stuff. All right, and then these are the lovely equations that go along with ocean acidification. So you also have these on your worksheet, and what I want you to look at is the top one is the direct contact with the water. So you're creating an acid when this happens. So this is carbonic acid in the first one. In the second equation, the reaction is the carbonic acid, and it reacts to produce a bicarbonate and a hydrogen ion. And then in the end, the hydrogen ion attaches to a carbonate ion to create another bicarbonate ion. So it's kind of messy and complicated, and the one thing that I really want you to look at is the last equation, where you have the hydrogen ion attaching to a carbonate ion to produce that bicarbonate, because you'll notice in the final reaction down here, it also requires a carbonate ion. So like in my last example, if I'm trying to make cheesy eggs and I don't have any eggs, what am I going to get? I'm just going to get cheese, right? So if all of this ocean water is reacting and taking up the carbonate ion, I'm not going to have any carbonate ion when I'm trying to make my shell. So this last equation, if I don't have any carbonate, what's going to happen? Does anybody think they can? So in the during the shell building process, if all I have is a calcium reactant, what's going to happen? What do you think, Britta?
Strong shells or no shells.
Yeah, you're not going to get strong shells or any shells because there's no carbonate ion to react with. All right. This last one is a video, and while you're watching it, I want you to think about some sources of problems, and then think about the solutions that the ocean acidification video talks about. So there's some problems that it talks about, and then it comes up with some solutions for those problems. So just jot down your ideas on that. Ooh, that did not work.
Scientists refer to ocean acidification as the other carbon problem. The first, of
Can you guys
course,
hear it?
is global warming.
People have heard about global warming for decades, but it's only over the past 5 years that experts really understood that the carbon dioxide is causing the problems with the oceans as well.
When we burn coal, oil, and gas, we introduce carbon dioxide into the atmosphere. But the atmosphere touches the ocean over 70% of Earth's surface. So this carbon dioxide we're putting into the atmosphere, we are also putting into the ocean.
What happens when so much carbon dioxide, 22 million tons of it each day, mixes with ocean water? In terms of chemistry, the answer is simple. It becomes an acid.
Since the Industrial Revolution, the ocean acidity is increased by 30%. If we continue to pollute as we are now, the ocean acidity will double by the end of the century compared to pre-industrial times. That is a big problem.
Thousands of ocean species build protective shells to survive. These organisms create their shells by drawing certain molecules from the water around them. But rising acidity depletes those molecules. And when acidity gets too high, shells dissolve.
We know that coral reefs are particularly sensitive to ocean acidification, and the reason for that is that corals are unable to form their skeletons as quickly as they used to, and reefs are starting to crumble and disappear. We may lose those ecosystems within 20 or 30 years. And in those structures live an estimated 1 million species.
There's growing alarm that higher acidity will extinguish creatures that are a basic food source for fish. In many parts of the world, fish are a basic food source for people. The only way to stop acidification is to emit less carbon dioxide. But the ocean can better defend itself against rising acidity and temperature if its systems